Bismillahirrahmanirrahim. We are discussing this course here, discrete structures. We will divide it into 16 videos, one or almost time for each video. Discrete versus continuous. Both of both of the definitions are in practical life examples of discrete data. Number of boys in the class, number of candies in the packet, number of suitcases lost by an airline. These are all the discrete data. We will discuss about the continuous data, height of a person, time in a race, distance traveled by a car. These are all continuous. What is discrete structure? Discrete mathematics is the part of mathematics devoted to the study of discrete objects. This definition was given by Kenneth H. Rosen in the 6th edition. Discrete mathematics is the study of mathematical structures that are fundamentally discrete rather than continuous. Wikipedia. Applications of discrete mathematics. There are a lot of applications of discrete mathematics in real life. For example, how can a circuit that adds two integers be designed? How many ways are there to choose a valid password on a computer? Shortest path between two cities using transportation system? How can I encrypt a message so that unintended recipient can read it? How many valid internet addresses are there? How can a list of integers be sorted so that the integers are in increasing order? There are a lot of applications. We will discuss about the syllabus. These topics will be covered in this course: logic, elementary number theory, set theory, relations, sequential recursion, mathematical induction, counting, relations, graphs, and trees. These are the references books which you can read for further. First is the logic. In logic, we will discuss about the propositional logic, logic of compound statements, propositional equivalences, conditional statements, logical equivalences, valid and invalid arguments, applications of digital logic structures, predicts and quantifiers, logic of quantified statements. Propositional logic. A proposition or a statement is a declarative sentence, that is a sentence that declares a fact that is either true or false, but not both. For example, is the following sentence a proposition? If it is a proposition, determine whether it is true or false. Paris is the capital of France. This makes a declarative statement and hence is the proposition. The proposition is true. Propositions, examples of propositions here we also these are is the following sentence a proposition? If it is proposition, determine whether it is true or false. Can Ali come with you? This is a question, not the declarative sentence, and hence it's not a proposition. Another example, take 2 aspirins. If we say to anyone, this is an imperative statement, not the declarative sentence, and therefore not a proposition. Another one, x plus 4 greater than 9, because it's true for certain values of x. If we put as such as x is equal to 6, then it's true. Otherwise, if we put other values, for example, x is equal to 5, x is equal to 3, 4, 1, 0, negative, then it's not true. So it's not a proposition. Another example, he is a college student. Because truth or falsity of this proposition depend on the reference for the pronoun he. It's also not a proposition. Notations. These are the notations which are commonly used to denote the propositional variables, that is variables that represent propositions such as P, Q, R, S. The truth value of a proposition is true, which is denoted by the capital letter T, or 1 if it is a true proposition, and false denoted by F, or 0 if it is a false proposition. These letters will be capitals. Compound propositions. Producing new proposition from existing propositions, logical operators or convectors. These are the logical operators: not, and, or, exclusive, implication, by condition. These are the notations of this. It also be written as like this: negation. Okay. Negative of a proposition. Here we also represent the negation. Let P be a proposition. The negation of P denoted by negative P, also denoted by negation P, which I discussed in the previous slide, is a statement. It is not the case that P, the proposition negation P, is read as not P. So it's used for negative, not. The truth values of the negation of P, negation P, is the opposite of the truth values of P. Here is the examples of negation P. If we say find the negation of the following proposition P, today is Friday, the negation of this P, today is Friday, is it's not the case that today is the Friday. You can see that today is not Friday. This negation can be more simply expressed in this: today is not Friday. Actually, you have to negate the sentence. You have to statement, you can put the negative to the statement. Here 6 is negative. The negation is, it is not the case that 6 is negative, or simply you can write 6 is non-negative. It is a truth table for P. It's very important and it's play a key role in discrete structures. These are the values for P and these are the values for negation P. If P have value true, which can be written capital letter T, then, and negation P will be false, it can be written as capital F. If P is false, then negation P means true. Mean to say, you have to negate the proposition, you have to negate the value. If here is true, then it's false. If this is false, it's true. So you have to negate the value in the first column, which is P, which may be Q, R, anything. These are the operators. This is the symbol for negation, not. This is for conjunction. Now we discuss about and. It is conjunction. It's like a conjunction is like a intersection. Let P and Q, if these are propositions, the conjunction of P and Q denoted by P and Q, this is the notation, is the proposition P and Q. In English sentence we can write this. In discrete we can write in this form: P and Q. The conjunction P and Q is true when P and Q are both true, and is false otherwise. Mean to say, if P is false and Q is true, then P and Q will be false. For in conjunction, both should be true, then it's true, otherwise it will be false. For example, if we say find the conjunction of the propositions P and Q, where P, today is Friday. If we say Q is, it's raining today. If we want to find the conjunction of P and Q, so we can see that today is Friday and it's a raining today, P and Q. So we have to combine, basically you can see that you can combine both statements. Conjunction is the combination actually of both the statements, and both statements should be true if you want the result of conjunction true, otherwise it will be false. In the next we can see the truth table for AND. Binary operator used for AND is this, which we already discussed. This is the truth table for AND. These are the values of P, these are the values for Q. For P we can use first two values true and the next false. If we use three values, then the first three will be true and the next three will be false, and in Q alternative values. In the third column you can see if P true, Q true, then P and Q will be true, and in the second P is true but Q is false, so we can see P and Q is false. If P is false but Q is true, but because one is false, so the result is false, and if both are false, then automatically it will be false. So the main dependency of P and Q is on these values. These two values should be true. Disjunction or this or mean doesn't mean operation as such. This means or. It may be acting as union. If we discuss about the definition of this, let P and Q be propositions. The disjunction of P and Q denoted by P or Q is the proposition P or Q. This disjunction P or Q is false when both P and Q are false, and it is true otherwise. Mean to say, if one of the values P and Q, one of them is true, then the value of P or Q will be true. So no need to true both the values like that. Conjunction. Disjunction is someone is true, P or Q, P and Q, if both true are values, then P or Q is true. This will be false if both are false. Next we can see the example of disjunction. We can see find the disjunction of the propositions P and Q, where P today is Friday, Q it's raining day. Then the disjunction of P and Q, today is Friday or it is raining day. Mean to say it's the union. We can add these two statements. Today is Friday, it is raining day. In P and Q we use today is Friday and it is raining day. But in disjunction we use today is Friday or it is raining day. Mean to say it depends on the possibilities. It may be it is Friday or it's raining day. If one of them is true, then this value will be true. Truth table for or disjunction. Binary operator used for or is this, and this is the truth table for or. These are the values of P. If P is true, false, false, Q is true, false, then P or Q, one of these values is true because both values are true, so P or Q is true. Okay, P true but Q false, no problem, P or Q is true because one of these values is true, then this is true. P true, P false but Q true, then it will be true. If both are false, P false, Q false, then OR sign has no options to say it as false. So if one of the values P and Q is true, then it will be true. You can write it as true. So the major difference in OR and OR, in this, if one is true, you can write the disjunction is true, and in this both should be true, then you can write the values as true. Now exclusive OR, it may be written as XOR. We will discuss about the definition. Let P and Q be propositions. The exclusive OR of P and Q, the exclusive OR of P and Q, denoted by P, this sign Q is the proposition. The exclusive OR P or Q is true when exactly one of P and Q is true and is false otherwise. It will be true, is true when exactly one of P and Q. In both, from this, if one is true, then it's true, otherwise it will be false. For example, if we say find the exclusive OR of the propositions P and Q, where P, Atif will pass the course, like this code. This is the code of the subject CSC102. It may be, you can see here we use this for discrete structures. Q, Atif will fail the course. This is the course code. The exclusive OR is, now you can see the exclusive for these two propositions. The exclusive of P or Q, Atif will pass or fail the course. You can combine both these. Atif will pass or fail the course. CSC102. Now this is the truth table for binary operator is this, for exclusive is this, and this is the truth table. These are the values of P, these are the values of Q, and these are the values for exclusives P, Q. If both are true, then it is false. If one is true, other is false, then it is true. If one is false, second is true, then it's true. If both are false, then it's also false. So the necessary condition for true is one. If one would be true, then the exclusive statement is true, otherwise it will be false. These are the examples for OR or exclusives OR. The following propositions uses the English convective OR. Determine from the context whether OR is intended to be used in the inclusive or exclusive sense. First, Nabil has one or two brothers. Okay, a person cannot have both one and two brothers. Therefore, OR is used in the exclusive sense. Nabil has one or two brothers. You can easily read this statement. Nabil has one or two brothers. Is there any person who can say that I have one brother or two brothers? Mean to say, you have to say exactly that I have one brother or two brothers. So this is the example of exclusive. It's also an example of exclusive. To register for BSc, you must have passed the qualifying exam or be listed as an math major. It's okay. Presumably, if you have passed the qualifying exam and are also listed as an math major, you can still register for BCS. Therefore, OR is an inclusive. If one of these values is true, then you can see it's composite statements. Composite statements are operators that can be combined in any way to form new statements. These statements will be used in the next slides. You can see here statements and operators that can be combined in any way to form new statements. These are the values of P, and these are the values for Q, and these are the values for negation P, and these are the values for negation Q. Negation P means if P is true, then negation P false. If P is true, negation P false. P false, negation P true. P false, negation P true. And in negation Q, you have to write the negative of Q in this. If this is true, negation Q false. If this is false, negation Q means true. If it's true, then it's false. If this false, then this is true. Negation P or negation Q. Now we use these two columns. Okay. We have to operate the operation OR in these two columns. Negation P, negation Q. Both are false, so it will be false. One is true, negation Q is true. So we discussed in the previous slides that if one is true, then it will be true. And in this negation P is true, negation Q is false, so it's true. If both are true, so it will be true. This is the composite statement. Now these are the translating English to logic. I did not buy a lottery ticket this week, or I bought a lottery ticket and won the $1 million on Friday. Let P and Q be two prepositions. P, I bought a lottery ticket this week. P, I bought a lottery ticket this week. Q, I won the $1 million on Friday. In magic form, you can write in this form: negation P or P and Q. Negation P or P and Q. Negation P and Q means I did not buy a lottery ticket this week and I won the $1 million on Friday. Negation P and negation Q means both P and negation Q or negation P and negation Q. It implies I did not buy lottery ticket and I don't win $1 million. I bought a lottery tickets and I did not win $1 million. This is the lecture summary of this introduction to the course propositions, logical convectives, truth tables, compound propositions, translating English to logic and logic to English, which we will discuss in this. Now, this is the conditional statements. These statements are very important implication. The definition of let P and Q be propositions. The conditional statement P implies Q, implication Q. You can say P implies Q is the proposition if P then Q. Like in programming, you can see that if P then Q, if and then. These are major words in this implication. The conditional statement P, the conditional statement P implies Q is false. It will be false when P is true and Q is false, and is true otherwise. Is false when P is true and Q is false. When P true, then Q false, then it's true. Otherwise, it will be true. Where P is called hypothesis, antecedent, or premise, Q is called conclusion or consequences. Implication if then. We can draw here the table for P implies Q. Binary operator for this is this table. We here erase these. This is the truth table for if then. These are the values for P, these are the values for Q. If P have the values true, true, false, false, Q have the values true, false, true, false. Then P implies Q. If both are true, then P implies Q is true. P true, Q false, then it is false. If P false, Q true, then it is true. We discussed in the previous slide about the definition. If this will be P is true and Q is false, then it will be false, otherwise it will be true. If P false, Q, if P false, Q true, then P implies Q is true. If both are false, then P implies Q is true. I mean to say, if we say if this is false, then this will be false. It's okay. Then the result will also false. So we will focus on the values of P and Q. Conditional statements, biconditional. Biconditional statements, these are like the reversible reactions in chemistry. Let P and Q be the propositions, then biconditional statement P and P if and only if Q is the proposition P if and only if Q. You can say that if this will happen, then this will, or you can say if that will be happen, then the reactants was these. So biconditional, by implication statement P double arrow, you can write it as double arrow, is true when P and Q have same truth values and is false otherwise. Please take a note on this statement. when P and Q both have same truth values, then it is true, otherwise it will be false. So we will focus on the both values. If both are true, then it will be true, otherwise it will be false. If and only if, this can write this in mathematical form. It can also be written in double arrow like this. Binary operator which used is this symbol is this. Now this is the truth table for biconditional. These are the values of P, these are the values for Q. True, true, false, false, P, Q, Q, true, false, true, false. Now, because both values P and Q are true, then P, if and only if Q is true. If one is false, then it's false. For same values of both P and Q, if one is true, other is false, then biconditional is false. If the P is false, Q true, then you can see that the biconditional operator gives the value false. If both are false, we can see that this is false, Q also false, then the biconditional will result the value true. So the necessary thing in biconditional is the values should be same in both columns. Either they are true, either they are false. So we will focus on the similarity of the values on both the values in column, in first two columns. This will give the result true only when both values will be same. If one of them is false, then the result will be false. Statements and operators can be combined in any way to form new statements. We can also combine in these statements in any new statements like this. These are the values for P, these are the values for Q, which already we discussed in the previous slides. Negation P. Do you understand about this? Negation P? Yes, we discussed in previous slides. If this value is true, then negation P is false. If this value is true, negation P false. This is false, negation P true. This is false, negation P true. And in Q, this column is for negation Q. This value is true, then the negation Q is false. This value is false, then negation Q true. If this Q is true, then negation Q will be false. If it is false, then negation Q. So you can easily understand about the negation. Now we combined these two columns, negation P, negation Q, with OR. This is OR. If both are false, then this will be false. If one is false, other is true, we already discussed that it will be true. If one is true, other is false, then the result will be true. If both are true, then so there will be no problem, then the resulting value will be true. So in OR, we only find one true value. If we find one true value, then the result will be true. Equivalent statements, if we discussed about the truth table of this, you can see about this. These are the values of P, these are Q. Negation of P and Q, we make a combination of P and Q. First we make P and Q, then negation. P and Q, true, true, then P and Q will be true. If we use, we find if we have both values true, then P and Q have true, and the negation negates the true value in false. Now this value is true, Q false, so then P and Q result will be false, and the negation make this statement is true. One is false, other is true, then P and Q will be false, and the negation make it true. If both are false, then P and Q will be false, but negation make it false. Negation of P or negation of Q. Now first we make two tables, two columns, negation P and negation Q. If P true, then negation P false, Q true, negation Q false, then the OR between negation P and negation Q will be false. If P is false, negation P, if P is true, negation P is false. If this will be false, then negation Q is true. So the OR between these two will be OR. And similarly, in this case, this will become true and this will become false, and in OR combination this will result the true. And the last one, though both values will be true in negation, so in the in result OR combination we make it true. Negation P and Q biconditional negation P or negation Q. Now we use these two tables in biconditional. So both are false, then in biconditional result will be true. Both are true, this will be true. Both are true, this will true. Both are true, this will true. So in biconditional we studied that if both values in both the columns values are same, then the result will be true. Otherwise the result will be discussed as false. Two statements are called logically equivalent if and only if. It can also be written as if I double F. They have identical truth tables. The statements negation P or Q and negation P or negation Q are logically equivalent because these have the is always true. Negation P, this column contains all values true. Tautologies and contradictions. Now we discussed about the tautologies and contradictions. This is very important. Tautologies and contradictions. Tautology is a statement that is always true regardless of the truth values of the individual logical variables. It becomes always true, never it goes to false. For examples, we discussed about R and negation R. Negation of P and Q, biconditional negation P or negation Q. If S implies to T is a tautology, we write S implies T. If S implies T is a tautology, we write biconditional as double arrow sign S implies T. A contradiction is a statement that is always false, regardless of the truth values of the individual logical values. Contradiction, you can say contradiction is basically the criticism, you can say it always becomes false, regardless the truth values of the individual logical variables, whichever, whenever, what is the value, true or false, it always becomes false. For examples, R and negation R, this will always become false. You can also find negation of negation P and Q, biconditional negation P or negation Q. You can find the truth table for these values. Then you can see that in the last table it will be all values will be false. The negation of any tautology is a contradiction, and the negation of any contradiction is a tautology. This is very much important statement. The negation of any tautology is a contradiction, and the negation of any contradiction is a tautology. You can say if you negate any tautology, it's also contradiction, and the negation of any contradiction, this will becomes true, so this is a tautology. In tautology, all values are true, regardless whether the truth values which they are, but the answers are true. Now we here will discuss about the exercises of the of discrete structures, and which will increase your knowledge by using practice in these. We already know the following tautology. For example, negation P and Q, biconditional negation P or negation Q. This will be the nice homework for you, and show that negation P or Q, biconditional negation P and negation Q. You can also solve this exercise at home, and hopefully you will find a better result by using the previous truth tables which I have discussed in the previous slides. I briefly discussed these slides so for being a first lecture, so that you can easily understand all the values of P, negation P, Q, negation Q, conjunction, disjunction, conditional, biconditional. These two tautologies are known as De Morgan's laws. These two tautologies are known as De Morgan's laws. Now this is the exercise for you as homework. You can try it for yourself. Given a set A is, I here briefly explain the question for you for your easiness, so that you can easily solve the questions at your home. A is the set X, Y, and Z, and a set B is equal to 1, 2, 3, 4. Now what's the value of 2A cross 2B modulus? You can find this. Okay, I give answer here for your easiness, so that you can easily solve 2a cross 2b. The value of this is 2a dot 2b. 2a is equal to 8, because a has the elements 3, and 2b, b has the elements 4. 2 raised to the power 3 and 2 raised to the power 4. The multiplication of 8 and 16 is 1 to 8. Now this is the graph theory practice question for you. In order to minimize cost to the city, how should weekly garbage collection routes be designed for Detroit's 350 million households? You can easily find you can easily use these values with truth tables for this critical question. And in the next lecture, we will discuss about the inverse and conditional statement, inverse of conditional statements. We will discuss about the contrapositive of the conditional statements, hierarchy of the properties for logical, convective, negative of a conditional statement, and also the conditional statements and inverse of a conditional statement. These are very easy topics which will be discussed in the next lecture, and I briefly explain for you for all these definitions and terms. And next we will also discuss about the biconditional with more examples. We have already discussed a little bit, but in the next lecture we will discuss in details, and we will also discuss about the logical equivalence involving biconditional and the argument about this, and we will discuss about the valid or invalid arguments. So for till that the next lecture will come, you can read out these all the slides and listen carefully this lecture. So we will meet in the next lecture with these topics, and I hope you can easily understand this course while I try to understand all the topics in a very easy way, in a very easy manner, so that you can easily approach to the extreme concept of the logics for the discrete structures. This is too much easy course, not difficult, but somehow students will fear about this course, that this is too much difficult. No, it's very easy, simple, and it's very useful in mathematics and in all applications, especially in computer sciences, mathematics, engineering. This is very useful. So don't worry about our subjects. We will discuss all the topics in next video. So be careful until the next video will come. Thank you.